we're going to take this a little bit further and talk about a little bit more complicated conversions when we don't just have these simple one-step things. What happens when our conversions require a little bit more work, and what happens when they go in between different measurement systems like English to metric and back. So we'll get into that a little bit, and then we'll talk about using things like density to help with our conversions, and then we'll go to lab and we'll measure some densities and use that to understand some things about materials. So, questions before we get started? How's the homework going? Okay so far? All right, make sure to work through all that chapter 2 stuff. We'll be into chapter 3, probably not today, but definitely Thursday. And we'll have the first quiz a week from today. So beginning of class next Tuesday will be our first quiz on the chapter 2 and beginning of chapter 3 stuff, basically whatever we cover this week. All right. Sorry, I'm a little getting over a cold, so I'm talking a little weird. Okay, so just to refresh your memory, we use this factor label type system. It works because it's really a type of multiplication. So if you're multiplying meters on top by a fraction with meters on the bottom, the meters cancel and you're left with the new unit. So we practiced that a couple different ways, converting some different things. And now we're going to extend that a little bit further. So I have some examples. These are in the notes folder, by the way, so you can check them out, linked off of Blackboard. But let's say we wanted to do something like this. And actually, I'm just going to grab the question because it doesn't matter. That's multiple choice right now. How many pounds are in 3.5 kilograms? All right. So to do this, we would set it up the same way that we've just been doing the other ones. We'd say, all right, we're starting with kilograms because that's what the number that we're given. And we ultimately want to go with pounds. But the kilograms to pounds conversion is not one of the ones that's on our list. It's not one of the numbers that you have to know on Blackboard. So what happens if we encounter that? Well, you'd be given a conversion factor here. I'd have to give you the number that fits. But I might not give you the most convenient one because it's just whatever we have sometimes. So what if I told you 1 pound equals 454 grams? That was the conversion factor I gave you. So now we have to rethink how we're going to do this question a little bit, because we don't have a direct conversion factor to just set up the equation. So what are we going to do instead?
Start making the grid and have 1 pound in the left corner, and then 1 pound on the bottom, and then make a second conversion for grams to kilograms.
Yeah, we're going to have to take an extra step, right, in between kilograms and pounds to get to grams, because we know how many pounds are in a gram or grams are in a pound. So we need that extra step. So we would go, instead of just kilograms to pounds, we go kilograms to grams to pounds. Okay. Now, once you have your map, your little map of arrows of how to, what units to go next, then it's easy to set up the calculation because we're going to follow that exact order. So we're going to start with kilograms, get rid of kilograms by putting it on the bottom and instead have grams. Then get rid of grams and instead have pounds. Now we just fill in the numbers. So we start with 3.5 kilograms. Then we recognize that there are 1,000 grams in a kilogram. And finally, that there's 1 pound in 454 grams, or 454 grams in a pound. That's the number that we're given. So then to solve the problem, we're going to multiply by everything on the top and divide by everything on the bottom. So 3.5 times 1,000 divided by 454. And we get 7.7 pounds. All right, so see how that works when there's an extra step? Still the same procedure. We just put something else in the middle. If we want to check our units, they do indeed still cancel. So kilograms, kilograms, grams, grams, and we're left with pounds. Okay, let's try another one. How many liters of soft drink are there in 5.25 quarts? So we want to go quarts to liters. Anybody know how many liters is in a quart? Quarts in a liter? I don't know. Let's say we don't know. But one that I remember, you don't have to remember this, but I'll remember it to give it to you. I know that there are 3.8 liters in a gallon. Do you know how many quarts are in a gallon? 4, yeah. So we also know that 4 quarts is a gallon. So given that information, see if you can set up a plan to go unit to unit and ultimately figure out how many liters there are in 5.25 quarts. Now there's a couple different ways you can do this. So once you've gotten something, turn to somebody close to you and see if you guys did it the same, or if you came up with the same number but did it differently, or if you just got completely different results somehow. Let's see where it differs. All right, everybody got some? What kind of numbers you come up with?
4.98.
4.98? So in that range? Something around there? Okay, yeah. So how'd you set this up? What was your path of units here?
Quarts to gallons to liters.
Yeah, so we could use an intermediate of gallons here. Did anybody do it differently? So I'm going to show you both ways that you can do this. One, we set it up exactly as before. We just use gallons as an intermediate. So we've got 3 units to switch here. Start with quarts. Cancel quarts and get gallons. Cancel gallons and get liters. So that's one way to do it. Fill in the numbers. 5.25, 4 quarts in a gallon, 3.8 liters in a gallon. 5.25 divided by 4 times 3.8. 4.98 or 4.99 liters. Okay, there's a shortcut here. Anybody find it? So we needed an equivalence or an equality to tell us how many quarts are in a liter. We actually kind of have that based on what I wrote in red on the right there. If you think about that, if 3.8 liters is a gallon and 4 quarts is a gallon, we could actually set those two things equal to each other, right? So we could say 3.8 liters equals 4 quarts. Because if they're both a gallon, then they must both be equal. So then we could set this problem up just using this one, and it would look like this. So we could go directly from quarts to liters by saying 5.25 quarts. 3.8 liters is this. 3.8 liters is the same as 4 quarts. And it would actually equal the same thing. We're doing the same thing. Just kind of getting rid of those ones. So that's another way to think about it, that we now have a conversion that sets those things equal to each other. All right. Think you can do that? Maybe? Think about it? Okay. Try another one. Oops. Reorient here. The 6.5 meters converted to inches. Now, I'm not going to tell you how many inches are in a meter, but I am going to tell you that there are 2.54 centimeters, in 1 inch. So see if you can set up a plan and solve that using just that conversion and ones that you know in your head. All right, you got some ideas here? So what plan did you take this time?
I did meters to centimeters to inches.
Yeah, so if we don't have directly a meters to inches conversion, we can use one that we know, and we could say meters to centimeters to inches. Now the meters to centimeters isn't given, but that's one that's on that list on Blackboard, so that's one that you should know. So when we set that up, we can go meters to centimeters to inches. Start with our 6.5 meters, and then we know there's 100 centimeters in a meter, 2.54 centimeters in an inch. .5 times 100 divided by 2.54, about 256 inches. All right. Now remember, we skipped that section of part 2. We skipped that part of chapter 2 that deals with how to decide how many decimal places to keep or round off based on the type of calculation that you're doing. So if you have experience with that, doing calculations with significant figures, you can go ahead and do it. Or if it bothers you to not have a rule, talk to me and I can work through that process with you. But our general rule is just going to be just pick some. So keep it somewhere around what the rest of the question is. So if the rest of the question uses 2 significant figures or 3, stick to that, something like that. We're not going to be real strict about where you decide to round. It's kind of up to you. All right. So what is the biggest mistake you think people make when doing these types of problems, even if you haven't made any mistakes yet today? Where do you think the biggest, most common mistake comes in? If you were to guess. Yeah.
Accidentally put like another 0, like put it to millimeters instead of centimeters.
Okay, so just like not seeing the unit right and putting another 0. Yep, that happens, sure. What else do you think? Yeah. What? Yeah, flipping the units, that's really big. And even more so. So you'll notice when I set this up, I write the units down first before I put any numbers in. I really recommend that because it takes away the thinking about like, oh wait, which way am I supposed to do this? Like I know there's 100 centimeters in a meter, but do I divide by 100? Do I multiply by 100? If you put the units in there first, then it makes it easier to get the numbers in the right spot. But that's still the number one mistake that I see. So like that middle factor, 100 centimeters over 1 meter, sometimes you're just not thinking or you don't remember or whatever, and somebody puts 1 on the top and 100 on the bottom. You'll probably see me do it a couple times while we're doing these too. It just happens. So one way to prevent that is always ask yourself, how many of these are there in these? So if I'm looking at that middle section and I accidentally wrote 1 on top and 100 on the bottom, that means I'm saying there's 1 centimeter in 100 meters. And if I say that out loud to myself, it doesn't make sense. I know there's not 100 meters in a centimeter. There's 100 centimeters in a meter. So sometimes just saying that helps you get that right, that it's got to be 100 centimeters in a meter. And that's the number that has to go with that one. The other thing that can sometimes help but doesn't always work is just looking at your result and thinking about it. 6.5 meters, I mean, we all know approximately what a meter thick is. So 6.5 of these is whatever it is. If we had flipped those 2 numbers, we would have gotten 0.256 inches, which is 1/4 of an inch. So we know that 6.5 of these is not going to be the same as that, 1/4 of an inch. So if you look at those numbers and just say, well, does that kind of make sense in the same general range? It can help you make sure not to flip those. Yeah.
If we don't round, is it going to be a wrong answer?
No. You can now I would prefer that you not just write like every number that your calculator gives you if it's some huge thing, just because it's confusing. It's around somewhere. But you don't have to if you don't want to. Yeah. I would say leave around the same number of significant digits that you see in the problem is a good rule of thumb. All right. Let's try it a little bit different. How long would it take to fly from Denver to New York, distance of 1,631 miles at a speed of 810 kilometers per hour? Okay, so I'm going to give you a conversion. 0.621 miles is 1 kilometer. Okay. And see if you can solve this problem. It's a little bit different because now we're given a speed or a rate, kilometers per hour. So see if you can play with this a little bit and come up with an answer of how long it would take to fly from Denver to New York. So walk around and see what some strategies are that you've used. All right, looks like several people have worked this out. So what was your plan here? How did you figure this one out? You wanna tell us what you did?
You do kilometers into miles to find out the speed.
Okay,
Then you
The
divide
distance,
the
yeah.
amount of miles into your speed, and then you get like 3.24 hours, but then you gotta do the amount of minutes and seconds.
oh, yeah, or we could just leave it in a fractions of hours, that's fine. But yeah, okay. So how do you know you had to divide by the speed?
I don't know, it's just by hour.
Just made sense, yeah. Okay, thanks, yeah. So that works. Did anybody else do it that way? People? Yeah, so you convert first and then divide by speed. Yep, that's a totally fine way to do it. And it works, and great. I would like to show you a little bit different way that I don't know if anybody did, but this will help us, especially when we go to think about density next. This number, 810 kilometers per hour, we can really write that as a fraction, right? Like 800 kilometers divided by 1 hour, per 1 hour. Okay. And we can also think of it as like a conversion factor, like an equality almost. 800, this looks a little weird, but 810 kilometers equals 1 hour. Now that only works in the context of this specific problem, but it's a way to use the same techniques we've been using and translate them into a problem where we have to go from a distance, miles or kilometers, to a time, hours. We can use the speed because speed relates distance and time. It tells us how many kilometers are in how many hours. So thinking about it that way, we can set it up exactly the same as the other problems and think of it as a conversion problem where we go miles to kilometers and then to hours. So miles cancels, then kilometers cancels, and then hours. Let's fill in those numbers. So 1631 is miles. Our conversion factor tells us there's 0.621 miles in a kilometer. And then this weird kind of speed conversion factor tells us that there are 810 kilometers in 1 hour. So we can evaluate it like that and say that we cancel miles, cancel kilometers, and end up with hours. So 1631 divided by 0.621 divided by 810 is about 3.24 hours. Which is about 3 hours and 15 minutes. So do you see how I use that kilometers per hour conversion to do that? That's going to help us anytime we have to go from one type of a unit, like length, to another type, like time. If we have a factor like that, that can help us solve it in the exact same way. So let's try another one. This one's a little bit trickier because it uses some bigger numbers. The Voyager 2 mission is talking about Neptune. So radio waves are light, traveling at a speed of 3 times 10 to the 8th meters per second. So 300 million meters per second. If Neptune was 2.75 billion miles from Earth during those transmissions, how many hours were required for radio signals to travel from Neptune to Earth? So once again, we need to convert from miles to meters. And then we can use that factor to get us from seconds to hours. Does anybody know how many seconds are in an hour? How many seconds are in a minute? 60? So we can probably do that, right? We can take an extra step. So if we're planning this out, we're going to say, all right, we start with this 2.75 billion miles. That's how far it is away. We can convert that to kilometers using that same factor before that we used before, 0.621 miles equals 1 kilometer. Then we can get to meters because we know that conversion. And then we can use the speed to go from meters to seconds. So we can think of that number as that many meters equals 1 second. Then once we've got seconds, we can get minutes, and we can get hours. The other tricky part is dealing with the big numbers here. So 3 times 10 to the 8th, that's 300 million. 2.75 billion, what does that look like? How many is a billion? Do we know what that exponent would be? So there's a couple ways you could do this. You can just type it out with a bunch of zeros, like 275, 0, 0, 0, 0, 0, 0, 0, I think is what it is, for billion. Or you can use scientific notation. There's a little review of scientific notation in chapter 2, if you haven't thought about that in a while. But that's 2.75 times 10 to the 9th miles. That's what billion is, it's 10 to the 9th. All right, so see if you can set that up and work through this problem now that we've got a little bit of a plan. All right, who's having trouble with the big numbers? Ready? Get them into your calculator and stuff? Yeah. Okay, let's set this up and we'll talk about that. I'm gonna take a few more steps. So we'll go miles to kilometers, kilometers to meters, meters to seconds. That's using our new kind of speed unit. Seconds to minutes, and then minutes to hours. So that's a long one, right? But it's same thing, same process, same procedure, just a lot more steps. So all our units should cancel appropriately and we're left with hours. Now we can fill in the numbers. So 2.75 billion miles, that's 2.75 times 10 to the 9th. 0.621 miles in a kilometer, 1,000 meters in a kilometer. And then we use this number for our meters per second. So that tells us that there are 3 times 10 to the 8th meters in a second, 60 seconds in a minute, and 60 minutes in an hour. Okay, let's put that all together and try to find an answer. Now, if you're trying to put this in your calculator, some calculators do better with scientific notation than others. Mine, for instance, here, my little one, if I keep it on the little one, does not have any kind of scientific notation in here. So I can use what I know about scientific notation and say, okay, there's a 10 to the 9 on the top, a 10 to the 8 on the bottom. That means there's a difference of a factor of 10. So I could just ignore those factors and then multiply by 10 at the end. That's one way to do it. Or I could just type in the full numbers. So I could say 275, 0, 0, 0, 0, 0, 0, 0. That is 2.75 billion, I think. Divided by 0.621 times 1,000. Divided by 3 times 10 to the 8th is 300, 0, 0, 0. Divided by 60, divided by 60. And I get about 4.1 hours. Now, calculator use. You'll always be allowed to use a calculator in this class, but for quizzes and exams, you have to have an actual calculator. You can't use your phone. Just because there's internet and stuff on your phone. So grab a calculator. It doesn't need to be anything fancy, just a regular 4-function calculator should suffice. Once in a while, we'll need to deal with big numbers, but usually this kind of basic calculator is fine. Let me show you how to access scientific notation on a couple common calculators for those of you who haven't done this before. I'm going to make sure to read, there's a part in chapter 2 that goes through scientific notation if it's been a while since you had to do that. Can I borrow that one? So this is your pretty basic scientific calculator. This one does scientific notation. So to do that, so if we want to put in like 2.75 times 10 to the 9th, you go 2.75, and the scientific notation is this little thing that says EE. It's like 2 capital E's. So I go second EE, makes a little E, and then I just type 9 for 10 to the 9th. So I can use that as scientific notation directly like that. Graphing calculators also have a little EE. Just look for that, and you don't have to put in the 10, you just put it in the estimate. If you have an iPhone, I don't, so I can't show you, but if you tip it sideways, then it makes a fancier calculator that gets an EE. Otherwise, you can always download apps and things that'll help you out. But you should get some kind of a calculator for the quiz. If you don't have one or you're not going to be able to get one for the quiz, just let me know, and I'll bring one down from upstairs that you can borrow. But we don't have any calculators, like a set of them down here or anything. So if you don't have one, you'll have to let me know ahead of time so I can bring you one. All right, so that's conversion factors. I mean, this is a really tough one. I probably wouldn't give you something that quite that crazy on a quiz or exam. But are there any questions about this so far? You want to do more of? All right, then let's talk about density. And we'll still be doing this type of a problem, but just with one other piece. How would you define density? Okay, so we can define it by its units, grams per milliliter, or more generally, mass divided by volume. What about in words? Like, what is it a measure of? What does it mean for something to be more dense than something else? Do you have a sense of that? I would say it's the amount of matter or amount of stuff, that's the mass, in a given amount of space. And the given amount of space is usually 1 milliliter, which is the same as a cubic centimeter. So we've got this block here. I think I measured this the other day. This little square here, which I can't seem to get off. All right, so this is a cube that's 1 centimeter on a side. So that's a cubic centimeter. And that is 1 milliliter. That's defined as 1 milliliter. So the amount of mass in this much of any substance is what we call its density. So we can calculate the density by dividing grams by milliliters. That will give us the density. Or we can use the density in a conversion problem to calculate something else. Does anybody know the density of water? Right. So water, the density is 1 gram per milliliter. Couple ways to write that. We could write it like that, 1 gram per milliliter. We can write it as a fraction, 1 gram divided by 1 milliliter. Or we can set it up as an equality. 1 gram of water is 1 milliliter of water. So just like those speed questions that we did before, this can give us a way to calculate something of a different unit. So if we have a mass, we can calculate a volume if we know the density. If we have a volume, we can calculate a mass if we know the density. And so we'll use that in a couple different ways. All right, let's practice that by working through some problems together. Not that one yet. Let's try this. This is very similar to what we're going to do in lab today. A nugget of gold with a mass of 521 grams, be a very expensive gold nugget, right? That's more than a pound, is added to 50 milliliters of water. The water, we're not going to do this experiment because we don't have that much gold. The water level rises to a volume of 77 milliliters. What is the density of the gold? Okay, so let's think about what's happening here. We've got this gold nugget. We put it in water, in 50 milliliters of water. The water level goes up. What causes the water level to go up?
Displacement from the gold.
Yeah, the displacement from the gold. So the space that the gold takes up is now down in the bottom of the water. So the water has to go up higher to compensate for that space that's now taken up by the gold. All right, so we've got a mass, 521 grams. How do we get a volume so that we can divide the mass by the volume and get the density?
Subtract 77 and 50 because that's the volume that the actual gold is taking.
Right, so if we imagine our graduated cylinder here, okay, there's our water at 50. We put in the gold. I don't have yellow, but we'll say it's green. Now the water is up at 77, and the gold is in the bottom. So the difference between those two levels is the volume of the gold. That's how much space the gold takes up. That's going to be our volume of gold. So 50 milliliters from the water. Anything else is caused by the gold. Okay, so now we have a mass, 521. We have a volume, 27. We can get a density. Density is mass over volume, which means 521 grams divided by 27.0 ml. 521 divided by 27 is 19.3. And that's the density of gold. So this is exactly what you're going to do in lab today. For part of the lab, you're going to put unknown metal cylinders in water and measure the displacement, and then try to figure out what type of material they are, what type of metal they are by comparing their densities to a chart. You're also going to calculate density by measuring the cylinders with a ruler. And this is always kind of a confusing part of the lab, but it asks in both places. It says, okay, first measure with a ruler and calculate the volume, and then see what kind of metal it is, and then do the displacement and do the same thing. The point is that one of those methods is going to be more precise than the other. The dipping in water is probably going to be easier, as you'll see, than trying to measure this thing with a little ruler. So you'll probably get slightly different results, and that's okay. Because when we use a more precise tool, we might get different results with the more precise one. Okay. So that's how you calculate density in that way. Let's try this one. Two related questions now. What's the volume in milliliters of a cube that's 1 inch on each side? And then if the cube weighs a certain amount, what would its density be in grams per milliliter? So first, in order to do that, we need to do some conversions because we know how to deal with milliliters and centimeters because a milliliter is a cubic centimeter, but we don't know about inches. So 1 inch equals 2.54 centimeters. And now see if you can calculate the volume of that cube. If you got the volume of the cube, go ahead and see if you can calculate its density in grams per milliliter. If not, just wait a couple minutes and we'll go through it together. Got some ideas? Think about it? All right. So how do you calculate the volume in milliliters if all you're given is a length? Anybody come up with an idea for that strategy?
1 milliliter equals 1 centimeter cubed.
Right. So we can use this equivalence that 1 milliliter is the same as 1 cubic centimeter. And so that way, if we can take 3 sides of a cube or just one side and cube it in centimeters, then we can have milliliters. So we use this equivalence to say, okay, that 1 inch, that's the same as 2.54 centimeters. So a cube, I can draw a decent cube here, that is 1 inch on a side is also a cube that is 2.54 centimeters on a side. So the volume of that cube is 2.54 centimeters cubed. Well, I don't have a cubed key on my little calculator here, so that just means it times itself 3 times. So 2.54 times 2.54 times 2.54 is 16.4 cubic centimeters. And since a cubic centimeter is a milliliter, then we know we have 16.4 milliliters also. Questions on that? All right, so then how do we do the next part? If we're given the mass of that cube, what would its density be?
The mass divided by the 16.4.
So 540 divided by 16.4?
No, because it's centigrams, not grams.
Yeah, centigrams. That's a weird unit. It's not one that we use a whole lot, but we can use our definitions of conversions to help us out with that. So we can say we want to go from centigrams to grams, and that gives us something like that, so that centigrams cancel. So how many centigrams are in a gram, or how many grams are in a centigram? We know that?
100 centigrams are in 1 gram.
Right. Remember that these metric prefixes apply to all units. So 100 centimeters in a meter, 100 centigrams in a gram. So that's 0.540 grams. And that means that our density is 0.540 grams divided by the volume, 16.4 milliliters. .033, we'll say, grams per milliliter. So what would happen to that object if you threw it in water, that cube? What would it do? What? It would float because it has a super low density, way lower than water. So we would expect it to be way up on top of the water. Yeah. If we look in the book here, there's a neat picture. Chapter 2. Right here. Okay. We see some objects floating in the water there. So water has a density of 1. Then you see some things with a greater density, aluminum and lead, which sink to the bottom. And then things with lower density, ice and cork, which float up to the top. You'll notice the ice is floating, but just the barest corner is actually sticking out of the water, whereas the cork is really floating way up on top because of the relative densities there. Cork is much less dense. So this one that we just solved, whose density is 0.03, it's like a super, super small density, would be way up on top. It would be like putting a balloon in the water or something where it's just right up on top. All right, so that's density. Let's solve the other type of a question, which I didn't have in that other list, but we can pull it here from the book. This one. All right, 2 teaspoons of cough syrup. If the syrup had a density of 1.2 grams per milliliter, and there's 5 milliliters in a teaspoon, what was the mass in grams of the cough syrup? So this one uses density, but we can really think of that just as another conversion factor. We're starting with teaspoons, and we ultimately want to get to grams. Now there is no teaspoon for gram conversion, so we have to go teaspoon to milliliter, and then we can go milliliter to gram, because the density tells us how to relate volume, milliliters, into mass, which is grams. So if you ever see a problem where you've got to switch from volume to mass, or mass to volume, you know the density has to get in there somehow. The density has to fit in there somehow. Okay, so now we've got our map. Let's write it out. So that's going to be teaspoons, cancel teaspoons, and get milliliters. Then cancel milliliters and get grams. 2 teaspoons, and then we're told that there are 5 milliliters in a teaspoon. And the density tells us 1.2 grams per milliliter. So we evaluate that out. 2 times 5 is 10. 10 times 1.2 is 12. So 12.0 grams of cough syrup. Now, when you've done this in the past, you may have been told something like, here's when you divide by density, or here's when you multiply by density. I think that that's confusing, and it's not worth memorizing. If you keep track of the units like this, you'll always get it right. The number for density, whatever the number is, like 1.2, always goes with the grams, and the milliliter always gets 1, because it's grams per 1 milliliter. So as long as you track your units and cancel accordingly, you can always make sure that it's on the right side, either flipped or, because if we wanted to cancel grams and get milliliters, then the 1.2 would go on the bottom with the grams, and the 1 would go on top with the milliliters. So just follow your units, cancel appropriately, and you should be in good shape. Okay, let's try another one. You try one. I can find one here. Fish tank holds 35 gallons of water. Using the density of 1 gram per milliliter for water, determine the number of pounds of water in the fish tank. So we've got gallons, we've got pounds, but our density is in grams per milliliter. So let's look at some conversion factors that we're going to need to put in there. We need to know that there are 3.8 liters in a gallon, and 454 grams in 1 pound. Okay, so with those two, see if you can set up a conversion and figure out how many pounds of water would be in this fish tank. So did you come up with a map like this? Gallons to liters to milliliters to grams to pounds. Yeah? All right, great. So we can set that up. Gallons to liters to milliliters to grams to pounds. 35 and 3.8 liters for a gallon, 1,000 milliliters to a liter, gram for a milliliter, and a 454 grams for a pound. Calculate that out. 35 times 3.8 times 1,000 divided by 454. I'm ignoring all the ones because anything multiplied or divided by 1 is just the same as itself. So that tells us 293 pounds in that water. All right. Okay. So that's density. I want to look at one other quick problem here that is less of a calculation. Find the right one I'm looking for here. Here we go. So this is like a matching question. Let's just look at it all together. So we're going to say which one is which here. We've got a solid with some density in some water. So what would we say about number 1? B? Why B?
Because it's floating, so you know it's less than 1.
It's floating, so it's got to be less than 1. But is it B or C? How do we determine that? Is it between 0.6 and 0.8, or is it half the density of water?
Probably half, it's half.
Yeah, because you can see the cube is about half submerged. So that tells us that's probably half the density of water. What about 2?
About the same.
Same density, right? Because the cube comes right up to the top, but doesn't actually go up above the water. What about 3? A, greater density sinks. And then 4 is going to be that B, because it's floating, and some of it is out, but it's not halfway out. So we would say it's between 0.6 and 0.8, something like that. All right, great. Okay, we're going to stop there. A couple things I want to show you first that I updated on Blackboard. If you haven't checked them out already. If you go into course materials now, so the schedule hasn't really changed. The lab stuff is still the lab stuff. Hopefully everybody's ready for today. I added this for class notes, so you can see the notes. That's where I'll be uploading the notes for the different sections, and then any like practice sheets that are in both sections will be here. So our section is section 5. You'll see our notes in there. The program that I used to use to automatically update it, like as soon as I write it on the screen, broke. It doesn't work anymore because of an update. So whenever they fix that, I'll get that in. Otherwise, I'm just going to be updating it myself. Also, we've got videos. So starting last night, I'll record all the classes. So if you have to miss, if you're sick or something, you can catch up there. Those will always be available unless there's technical difficulties or something. And those are actually live. So if you're home like at this time, you can still be watching the class, even if you're not here. So hopefully that's helpful. I'll see you upstairs in about 20 minutes. Don't forget about everybody's dressed appropriately. Everybody's got pants or closed-toed shoes if you're not wearing them right now.